Hello everyone, in this video we are going to look at what is the reaction mechanism of Wolff-Kishner reduction. So for the Wolff-Kishner reduction, the reagent what we are using here is called hydrazine. So it basically is the nitrogen-based nucleophile. So when you have a ketone or aldehyde, what we are going to put here is your hydrazine, which is a nitrogen-based nucleophile. Because it's nitrogen-based nucleophile, this reaction also needs to be acid catalyzed, and at the same time we do need to remove the water in order to drive the reaction to the right side for the completion. And then after that we do need to introduce the base and allow time it need to be in the aqueous solution and heat it up. So what's going to happen here is it will be the ketone will be reduced to alkane. So reduce the number of carbon-oxygen bond, increase the carbon-hydrogen bond. So now what we are going to look at is the reaction mechanism. When you have acid catalyzed reaction for the ketone and aldehyde, the first step, we are going to make our carbonyl carbon more electrophilic by proton the oxygen. So what we are going to have here is a positive charged oxygen at the end of the product that makes this carbon right here very electrophilic. So now we have a relatively not so strong nucleophile hydrazine, and on here we do have lone pairs on nitrogen, so this nitrogen lone pair will attack, and that is the general reaction mechanism of the acid catalyzed nucleophilic addition. So what we are going to end up here is that tetrahedrous structure intermediate that have the nitrogen form the new bond. At this moment, nitrogen have two hydrogens, so nitrogen will be a positive charge and still connect to the other nitrogen. Now this nitrogen has positive charge, so the base will come in to deprotonate. You may ask what this base can be. We have water floating around that come from the first step, so the water can come in to grab this proton, and that will deprotonate this intermediate. Now we have a neutral nitrogen with another NH2 connect to this nitrogen. So the next step is we are going to kick out of this OH group by protonate the OH to make it a better leaving group. So now what we have here is again we have hydronium in this step, so it will go to grab a proton, and now what we are going to have is a good leaving group water, and at the same time we have nitrogen with a lone pair and nitrogen bond. So no surprise, this will be very similar to when you have the nitrogen base nucleophile, for example the primary or secondary amine is going to kick out the leaving group, so you are going to have a carbon nitrogen double bond that will be formed. I'm going to draw that out. I'm going to have this nitrogen now have a hydrogen still and form that double bond, and then at the same time it will be positive charge and also connect to NH2. Now what we have here is an intermediate that still has this positive charge, so no surprise, the next step is we are going to have a base to come in to deprotonate to make a neutral species, and also this actually recover our catalyst, so water comes in and that will give us a neutral species. This molecule will have a nitrogen carbon double bond, and also the nitrogen still will have an H2 connects to. Let me write this out as showing the bond right here. So N hydrogen and hydrogen. So this completes the first reaction that we have a nitrogen-based nucleophile under acid catalyzed condition. Remove the water. This is our product. And this reaction also regain your catalyst. That's why we call it acid catalyst. So the next reaction is where this reduction really happens. And how it happens is we have a base introduced. So this base is hydroxide. Okay, so on this oxygen lone pairs. So this hydroxide will come in to grab one of the proton on this nitrogen. And that pair of electrons will push over to this nitrogen. Okay, this nitrogen. So that will give us the intermediate for the next reaction, reaction number 2. So at this moment, the nitrogen will have a lone pair. Now it basically have 2 lone pairs with negative charge, because before it had 1 lone pair already. So this lone pair will be resonance stabilized. So it will have the resonance. That will be resonance stabilized, like lone pair on this carbon, now negative charge, nitrogen, and we'll have this double bond. And next step is very cool. You have this resonance stabilized lone pair, and we notice that on this carbon it have this negative charge. When carbon have negative charge, it's very, very basic. So if you have water floating around, it will go and grab this proton to make it neutral. So what we are going to get here is now I have a neutral species, this blue one. And the next step, what we have here is a base. So the base will grab another proton again. Let's use the blue color, maybe yellow. And you have hydroxide. So this is the driving force of this reaction. Really cool that it will grab this proton. And at the same time, it is going to go over to form this bond, and at the same time this will break. So what is forming here, going to go this direction now, is to have a very, very reactive carbon base, and you also have nitrogen with a triple bond, which is a gas, that is nitrogen gas. So this reaction will bubble up. This driving force is to form this gas and coming out of product side to driving the reaction to the completion. So the last step is what we have is water. So the water will give a proton to this carbon, so it will get this proton, and that will get us to our final product. So that is the reaction mechanism of Wolff-Kishner reduction. So the first reaction what we have here is basically a nitrogen-based nucleophile under acidic condition. Nuclear proton transfer to make a more positive charged carbon, more electrophilic. So a relative okay nitrogen nucleophile will be able to attack, and through several rounds of protonation, deprotonation, that we form the product of the first reaction. And by introduce the base, the potassium hydroxide, and in the aqueous solution, we will be able to reduce this ketone to the final alkane as a reduction reaction. So that is the Wolff-Kishner reaction.